We are continuing with averaging. Let us start with the basic system. Very simple. It's scalar. It's in Lagrange standard form. Everything is good. And first order averaging or simple averaging, you just find the average of that. The period is 2 pi. So 1 by 2 pi, the integral from 0 to 2 pi of x sine squared d plus x dt. I hope you remember x held constant. Actually x changes, but over here symbolically it is held constant. So this part is easy, right? Because the x is a constant, the average of this is just half. And so we get x dot equals minus epsilon x by 2 as the averaged equation. Very good. The thing to note is that this is of the form x dot is equal to epsilon times some function of x. Now this here is dx by dt, and so you see really what we are saying is if we say tau equals epsilon t, then dx by dt is equal to f of x, and so tau is the appropriate time scale on which to observe the averaged dynamics of this system. Let us check that in MATLAB. So here we are in MATLAB. Let me put epsilon equals 0.1. I have already defined, I've written the system here, minus epsilon x sine squared t plus x. Over here let me close my figure. I will define OP to remind you that for all serious calculation you need to do this. Let me start up to a time interval of 1. Initial condition is 3. This is my function simp average. I do that here and I plot Tx. So here is tau. This is epsilon x, you see. So I make that plot. Here's the plot. Okay, so some function now. Now I say hold on. Good. Now I come here and I try epsilon equals 0.02, for example. And when I do that, since epsilon t is my time, I just made epsilon 1/5 of what it was. I will run this 5 times longer. And then I will plot this, but this time I will not plot it in blue. I will make this 0.02 and I will plot this in red. And here are the two curves. You can see that it's clear that they represent essentially the same average dynamics. In the blue case the wiggles are bigger, in the red case the wiggles are smaller and faster, but it's really the same curve. Okay, so they are catching the average dynamics, and by this numerical experiment it seems clear that the correct time scale is in fact epsilon t. Very good. Let's take a different system now. So the game becomes more interesting if we have this system. Okay, so now first order averaging gives x dot equals epsilon times 0. Okay, so we don't expect an order epsilon rate of change. no order epsilon rate of change in averaged dynamics. So let's do some numerics. Suppose, guess, that x dot is now epsilon to the power m times f of x for some f and some m. What that means is tau equals epsilon to the power mt is the appropriate time scale. Can we find this from numerics? Can we guess m? Let's do that first. Back to MATLAB. Over here I remove this square. I go back to point 1. I say hold off. I expect a longer time frame is needed, longer time period is needed to show me any change. So this time I will do till 500. This integration, and then I will plot this one, but I am guessing that maybe m is 2. Well, let us see first what happens with m equals 1. Okay, so here I have that. I do hold on, then I come here and I make this 0.5. I come here and make that, since I'm guessing 1, I should do 1000. And then I go there and I plot this one as 0.5, and then I plot that in R. Very good. Let's look at my figure. You see, these two curves are clearly different. The red and the blue are not following the same curve. Therefore, my assumption that m equals 1 is wrong. Let me get rid of the red curve. Well, let me just get rid of the whole thing. Doesn't matter. Okay, let's go back. So let us start with this epsilon equals 0.05. I have the answer. Let me guess that m is 2. What does that mean? I come here and I go 0.05 square. And I have a graph there. That's the graph. Very good. Now I come back here. Sorry, hold on. Then I come back here and I make this 0.1. So if epsilon is doubled, the time frame should not become half. Since I am guessing m equals 2, the time frame should be 1/4. I'll do that. So I'll come here and integrate till 250. And then I will plot 0.1 square, and this one I will plot in black. And you see it is clear that they are the same curve. You see they are the same curve. Therefore, m equals 2. Okay. So this is our motivation now. And now we are back to this problem. It is clear that what we need for this problem, what we need is something that will give us a second order averaging. In general, we need higher order averaging. The calculation is straightforward enough, and it proceeds with a more formal approach. More formal, general, powerful approach. It is based on a change of coordinates involving something called a near identity transformation. So let me show you that now. So here we are. X is my original variable. X bar is my slow variable. What I will do is I will pose a near identity transformation, which I will say is x is equal to x bar plus epsilon times some function which I have not chosen yet. I will choose this later. Let me call this W1, epsilon squared W2 of x bar and t plus epsilon cube W3 of x bar and t plus dot dot dot. You see, these are to be announced. But because epsilon is small, it is clear, because epsilon is small, it is clear that x and x bar are not far away from each other. And we will choose this in such a way that this will not have wiggles and oscillations in it. That's the game. How does the game proceed? I think I need to scroll down a bit more. So the game proceeds like this. X dot is equal to x bar dot plus epsilon del W1 del x bar dot plus del W1 del t plus epsilon squared del W2 del x bar dot plus del W2 del t plus dot dot dot. This is just elementary calculus. There is no trick here. The cleverness is here. Why it is clever will be revealed soon. This is just elementary calculus. Okay. So now you see that x dot and x bar dot also differ only by order epsilon. As epsilon goes to 0, these things go to 0. W1 does not depend on epsilon. This is the form of the transformation that we are posing. Very good. X dot is equal to minus epsilon x sine t plus x. This was our problem. We will think of it as x dot equals epsilon f of x and t. This f, of course, is not to be confused with this f. This is just a notional idea here. This is also notional, but this is something that this is the general form. This is the specific example we are studying today. All right, very good. This equation must still hold. That's our main equation. So this, we should be able to substitute this in here. We do that. What do we get? On the left side we get x bar dot plus epsilon del W1 del x bar dot plus del W1 del t plus epsilon squared del W2 del x bar dot plus and so on is equal to epsilon f, and here the fun begins. Okay, I think you really need to pay attention to this and sort of understand the structure. All the x bar dots are still on the left hand side. This right hand side I have substituted the NIT, the near identity transformation. This is the differentiated form of the near identity transformation. I still haven't said what these are, but whatever they are, whatever I choose them to be in the future, it does not matter. This orange box has to be true. Okay? Now here is the interesting thing then. You see, because here is x bar dot. This is order epsilon, this is even smaller, this is order epsilon. Therefore, x bar dot is equal to order epsilon also. X dot was like x dot. Okay? What have we gained? What we have gained is this. Since x bar dot is order epsilon, let me say x bar dot is equal to epsilon a1 plus epsilon squared a2 plus epsilon cube a3 plus dot dot dot. Let me pose this. These are expressions. They are functions in terms of x bar only, because that is the averaged variable. We are going to average the time out, right? So this one, this one, this one, these depend on x bar, but these are expressions that we will determine. Okay, so when we have that, then we come here, this one here, this one here. What the interesting thing that happens is that this one becomes epsilon a1 plus order epsilon square. This one being epsilon a1 to begin with, and this having epsilon, this moves to this order. In this order, we just have del w1 del t. That's really important. Okay, so we come here and we get epsilon a1 plus epsilon squared a2 plus dot 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 plus epsilon del w1 del x1 epsilon a1 plus dot 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 plus del w1 del t plus epsilon squared, and then this is order epsilon. This is the del w2 del x bar, and then plus del w2 del t something is equal to, and then let's look here to make sure that we are not making a mistake. Let's look here. This is the part we want, and so we get epsilon f x bar t plus order epsilon squared. That's the key part. I'm going to take this expansion in Maple, so you will see how that works out. But what is really important is that at order epsilon, I have this multiplied by this, I have this. Why is this order epsilon squared? Get used to it. This is the change from x bar, right? So this epsilon and that epsilon make it epsilon squared. At leading order, only this x bar remains. Okay, good. So at order epsilon, I have a1 plus del w1 del t is equal to f of x bar t, and higher order terms will come. Will be dealt, dealt with later. Let me pause here.